Okay. Hello, everybody. Today we want to talk about the applications of the filtering of images in the Fourier domain. And for this one, we're going to cover a couple of examples. But before we start with the examples, we want to give a general idea of the Fourier transform, or the transform in the Fourier domain. Now, let's assume first of all, if we have a signal which is a one-dimensional signal, okay? It's a continuous one, and something that could be the last thing that you might forget in signal and systems course or anything that regards with the transform domain would be the following. So you may forget a lot of things, but the last thing that you could forget is that the Fourier transform of a Gaussian function will be another Gaussian function. So if you come from this domain to this domain through a Fourier transform, we should get a Gaussian. If we go backwards with inverse Fourier transform, we should get a Gaussian again. So this would be considered like inverse Fourier transform. Okay. So now let's try to explain what we have here on the board. So we call this one the real domain. Okay. So this is the real domain because these are real numbers, and these are things that we can measure using a device which measures anything but the phase. Okay, so phase ose faza është një element I cili është ekuivalent me numrat kompleks. So this is the real domain, and this domain here, this is called the transform domain, or we can call this one or the complex domain. Now, this complex domain, using the keyword complex, it would be a good choice because the numbers that we have here, they are all complex numbers. Now, complex domain is just for good reference. Okay? Then we can call this one transform domain, which is it's not a synonym, but transform domain, which means that any transformation that we do on the data set, we call it transform domain. A more specific case in this course that we are dealing with today, this is the Fourier domain or Fourier transform, Fourier domain, or the case space, or the reciprocal space. So this can be also called the reciprocal space or domain, or conjugate. Okay, so we have we have quite a few synonyms for this important concept. So we call these also the conjugate domain or conjugate space. Now, regarding these, let me have a look if you are seeing all of these here. So regarding these synonyms, now let's understand what we have here. So we have a signal, we take the Fourier transform, and right away, what we get, we have this complex domain, we have separated it into, we can separate this one in two different domains also. So the first part, this one in the middle, we can call this one the mathematical construct. Okay? So we call this one, let's call this one mathematical construct. Okay? So this is something which is a metaphor. Okay, so this is a good word to pick up. Not only a metaphor, but it's a mathematical construct, which is only in the numbers. Okay. Now, I can discuss more in length regarding why we are separating this in two different domains. But for now, I think I can keep this short. So we can call this one mathematical construct, and this other domain we can call this one experimentally measurable. Which means this. We know for sure that the signal in the real domain, if it's a Gaussian, if we come here in the transform domain, if we measure the phase or the components as a function of the k vector, it's going to be a Gaussian too. Okay? And often, when we measure something, we do calculate something which is different from the mathematical construct. Now, I'm trying to make this one a little more clear when we discuss about the filters. So, this domain, which is called the mathematical construct, we can go to the next experimentally measurable. So this is also like half a metaphor. Okay. So we need to shift the data. So from here to here, we need to do a shifting of the data so that we measure, we see exactly what we want to see, or to make it more obvious. Now, or to see the complete thing. So in principle, let's explain this part. From here to here, what we are doing, we are taking the Fourier transform, and the numbers, they are everywhere like this. And when we do this FCT shift, what we are really doing here, we are first applying an absolute value of the function. So all of these, they come like this, okay? So these values, which are like the absolute values of this function, which was in black, then we do the shifting, and once we do the shifting, we construct this Gaussian function, okay? So now similarly, we have an image. If it is, we take the Fourier transform in 2 dimensions, we get this mathematical construct. When we do the shifting, this edge, which is in red, it will come here. So if we divide this one in 4 pieces, like this part will show up in here. This edge, which is in blue, it will come up right here. And this edge, which is discontinuous, it will come up right here. So this is how the shifting will go on. Now, let's move to the examples. To a couple of examples. Let's share the entire screen. Okay, so let's have a look at what we have here. So first of all, let's clear out some let's clear out the space that we have. So after this short general discussion about the Fourier transform, let's see how can we apply these techniques in the Fourier domain. And in the Fourier domain, the major interest that we have is to apply specific filters. In the previous 2 weeks, we discussed about the filters in the real domain, or where we were doing element-wise multiplication of specific kernels with patches in the images that we had. Now, let's see what we have here. Let's read this. I have this money JPEG. Let's see what this is. Money, it's like this. Okay, finally. Okay, so here we have some money, Albanian money, and with this Albanian money, probably it took us quite some time. It's not easy. Okay, and let's start actually with some. Let's say money. This is 500 lek or 50 lek. And let's this money 50 JPEG. Okay, so here we go again. Okay, so here we have a banknote from an old Albanian banknote
from the before the 90s, and then we have this image, but this one it's with noise. Okay, there is some noise on top of that, and what we can do after, let me see. So first of all, this image, this is 256 by 320, so this is unsigned integer 8. Then we find we want to do the padding on this image when we manipulate this image in the Fourier domain. And if we notice, we see that we have constructed a matrix which is twice the size of the image itself. Okay, so from 256, 320, we get 512, 640. Now with these, what we do is something that we wrote before a while on the board. We said that the image, what we do, first we convert this into double variable, then we take the fast Fourier transform in 2 dimensions, okay? So we take the Fourier transform. So far, if with what we showed on the board, we are here in the mathematical constraint. So we are in this part of our complete analysis. So if we do this, then we apply, let's check this part, we do the evaluate the selection. So so far we take the Fourier transform and we try to have a look at it. And here it is. Okay, so the Fourier transform of this image, here we have it. And then this image was actually a relatively low quality, and all of the rest, they are almost doing the same, showing the same thing actually. So just that it looks a little better. Evaluate the selection, figure 134. Okay, that's the same image. So here we see the variables. We have this f, which is the fast Fourier transform, but it's not shifted or anything. Then what we can do is that we can also plot. So these 3 lines. So as you can see here, we can see the image in the experimentally measurable domain. Now that's a term I'm using in this course. And then, so this f that we had before a while, we just shift it and we want to plot it. Okay, so if we plot it and we want to, after we shift, this is what we get. So in principle, whenever we take, so this was the image which was not shifted before, okay? So this one on the left side, the small one for the moment, this is the shifted version. So we had the image, we took the fast Fourier transform, and we get this figure 134. But then we need to shift it to go to the experimentally measurable, which makes much more sense for us. Because if you notice carefully, we have a lot of components, or we have a high intensity of the Fourier frequencies, or the Fourier domain, which are centered right here in the center. Okay, so if you zoom in a little more, so this is what we observe. Okay, so we're zooming much more in here. But now, what we said before, we said that this is the shifted version, because this part on the top here, this is moved down here at the 4th quadrant, and this one has moved up. So actually, here in the edges, we cannot see it exactly, but here we have the highest intensity of the frequencies, or we can say that we have the highest amplitude of the k equal to 0 frequency. So right here in the middle, we have the lowest frequency terms, which makes sense. And in the k domain, always the frequency components, they are shown symmetric with respect to the 0. Okay, so we show the low frequencies and then the higher frequencies. So that's why we show them like this. That's what I hope now it's clear what we mean with the shifted and unshifted version. But both of these 2 figures that we just saw, they were both in the Fourier domain. Now let's see what we had in the real domain. In the real domain, we had this. And it looks like, if we see this image, we see that we have some high intensity peaks, which are shown here, which are brighter than the rest, which might be a signature of periodic noise that we can have here in this original image. So now we have a look at the image. That's how it looked like. Now the next thing that we may want to do is that we want to have a look at how where these high frequency components are. For this one, let's have a look where the bright spots are, and with data cursor, we can go and sit and try to identify a region which has the high intensity, and we can read the values. So we observe this is 0.76, 0.78, 0.76. Apparently, this is 76, 78, 78. Okay, so it looks like this is a spot which has a high frequency. This is the location of this high peak. It's 50,100. Okay, so we go here, and if this is 5100, we want to generate a filter, but this is a notch filter. Now, this notch filter, the parameters, the way to construct this is the type of the filter, it's called the Butterworth. This PQ1, PQ2, this is the size, which is 512, 640. So this size of PQ, this is the dimension of the filter, which is going to be equal to the same size like the image that we have. We are manipulating it now. The width of the filter, it's 10. So we can construct a filter which has a width 10. We can make this a little higher. Let's make this 50 to completely clear, or let's make this 100 for a specific reason. And this was the exact location where this, where we had this high frequency in the Fourier domain. Now, notch filters are called filters which clear out completely a specific frequency. Imagine for a moment if you have white light coming from the window and you use a prism, the different frequencies are spread out like the colors of the rainbow. And imagine for a moment that a notch filter would be a filter which would clear out, let's say, the green light. So the green component in the filter, we can filter out with a notch filter. Similarly, like if you have a rainbow and you have a notch filter on your glasses or in front of our eyes, we see all the colors except the green. So we see the rainbow, all the colors, with a band which is completely missing. Now, this is how this was the location at 5100. Let's try to identify another location in the Fourier domain. So here we have a high peak, and the intensity is 0.79, 0.79. It looks like we found the. Okay, here we have it, 620, 100, 620, 100. So it's this other peak here, okay? And let's make the width of these filters 30, a little higher than what we have denoted initially. And these filters that we show here, that's one of them, we made it 100. So we look at these, we generate these filters. Again, it's a Butterworth with specific size. So we generate all of these here, evaluate selection, and here in the workspace, we can see all of the filters, H1 to H6. And now we can plot all of these filters to see how they look like. Now, since there are going to be notch filters, we are producing a specific zero at some, we want to multiply with 0 at some specific region, and we want to multiply with 1 everywhere else, okay? But these functions are not step functions, which means that they are smoothly generating from a 0 to 1, as we can see how gradually these are. And we can even try to plot this one, figure 111. Let's see, filter H1. So this is our specific filter. Since this is located right at the edge of the image, it's a little tough to see this one. But if we try to rotate this, we see that this filter, it's almost 0 right at this location. Okay, this is H1, and that we try to plot here. Now, these are the filters, and now what we do is that we multiply the image in the Fourier domain, which is this F. We multiply with all of the filters, and after we multiply, we can have a look at how the image would look like. So initially, if you remember, what is this? So initially, we had this figure 134, and here we have this image. Now, these bright spots that we had before a while, these specific bright spots, now they are darker, or we have wiped them out, okay? And now, let's, if we want to have a look from here, what we are really trying to do is that we're trying to make zero this spot, okay, this bright spot which is right here. But since this was the before the shift, so since this one is after the shifting, this bright spot that we observe right here, it's in fact here, where I'm moving with the mouse around. So that's good. We multiplied with a specific filter. And since we multiplied with a filter, and let's remember that this multiplication with a filter, we did it here in this domain, in the mathematical constraint. Okay? So we did it here. So that's why we are not using shifting at all. Okay? And in order to see how the image looks now that we cleared out some specific frequencies, we take the inverse Fourier transform and we get image clean. And finally, we get something like evaluate selection. What we get, this is the image that we get. Apparently, there was some noise on it, and now that noise is gone. But now, in the real domain, let's not forget that the image itself, it was half of the size that we are working in the Fourier domain. Now, this is figure 15, and we can have a better look at the image. So to have just so this is the image of interest, and let's see if we can find the figure 10, which was the initial one. So this was the filter, and this was the image 10, that we started with, and this had some noise that it looked like it was periodic because we have these specific high peak features in the Fourier domain. At the same time, this image that we tried, since there are also some periodic lines or features in the image itself, because there are some parallel lines everywhere, like this is a building where there are some parallel lines. And of course, if you try to be a little more selective, I see here there is also some bright spots around here. So if we try to wipe these out, probably we can remove some features in the real domain which are represented by parallel lines. So many parallel lines in the real domain would correspond to beautiful features or high peak features in the Fourier domain or in the transform domain. Now, these are, so this was, let's see, F was the Fourier transform image, and the FFT shift, this was the shifted version. But I think we already showed this one before a while. So this is, again, actually we already saw this, but apparently this is like the noise. And since we see here some higher peaks, which correspond, so let's notice for a moment. So we see a distance from the center up to here, which is somewhat in the order of tools, data cursor. So starting from the 0, the location here is 257. 257, let's go upwards, 257, and this is up to 257, 142. So we have 257 minus 142. This is 1, so it's 115. So we see a distance of 115 from the center to here, and look at this bright spot up here. This is also a bright spot which is somewhat as big as twice as what this term was here. Okay, so in the K space, we observe that we have two relative magnitudes of the K vector. So let's consider this one K0, and this is 2K0. So this is twice of what this feature is. Or pick up this one. The distance from the origin is K0, and this other point here is twice the K0. Now, what they correspond to, for example, this means that this K, which is large, this represents a small distance in the real image. And this k, which is smaller, this represents a higher distance, or higher spatial frequency in the real image domain, okay? So apparently, so this is how we can read these. So if you have some parallel lines which are very close to each other, then we see this peak, which is twice as some other distances which are farther away from each other. So that's how we try to identify these. Then we come back here, and what we can do from here is that we have, let me see for a moment. Now this image is the original image, and this imClean is the image that is filtered, okay? Now this image that is filtered, we can apply a function which is floor, so we want to get integer values for this image that is filtered. And then once we do floor, so we have, we make the variable unsigned integer 8, and we take the difference. Once we take the difference, what this could correspond to, this is the original image, this is the image which is filtered in the Fourier domain, and we are taking the difference in the real domain, okay? And what we can find from here, we can try to evaluate what were these noisy features. So apparently, let me see, this is f nu, so we have this function. So this 21 is figure. I guess this is log of c. Okay, so, and that was a periodic noise, and here we can see that this periodic noise, which was everywhere, it's something like, it's a random noise or periodic one, which has a frequency of approximately 10 pixels. So if this is around 300, what was the original image? It was 320. So the original image, it was 320. That's why we have this. And it looks like every 10 pixels or so, we have a noise which is moving up and down. Now, this was the application, or let's say the example with showing this image, but I may have to agree that this image was itself a low quality. It was not the best image. And this is pattern 01. Let's see this other. So we can clear most of the. So let's read this image here, which is a pattern image. And in the workspace, we can see that it's a size of 240 by 300 by 3. So it's a red, green, blue image. Then actually we can plot it like this, evaluate selection. So this is the image, which is a pattern image. Then we go here, we make this one RGB to gray, and we can see here that in the workspace that the variable type is slightly different. And let's do this image 101. So do we preserve the 10? So this is the original image in RGB gray, and this is grayscale. So this one is a grayscale. Maybe it's not very clear. Here we generate the padded size, which, as we said before, the padded size, which defines the size that we're going to manipulate the image in the Fourier domain in order to reduce the errors or the ringing effects. This is twice the original image of that we had before. Then we move on with the same techniques. So that pattern image. So all of these are equivalent, but let's show. But wait a second, we have not, here we take the Fourier transform, yes. Here we take the Fourier transform. Actually, let's have a look at all of them. So we take the Fourier transform, and here we are. We get So the difference between these is that we just use some operators to have a better look at the image. So let's close this one. Let's have a look back where we were, and let's assume that we plot the figure 12 without the scaling. That function is just, so as you can see from here, we can see nothing in this image because the intensities are at a high, the gradient between pixels at different points in the Fourier domain is so high that in order to have a look at those, we use this linear function, which is just a MATLAB thing. It's nothing tricky. But what is essential for us is that the original image, it was this, the Fourier transform is this, but we should say that always, if we have a structure in an object, we should have some low frequency components. Now, the low frequency components, they are here on the edges, okay? Because this is not shifted yet. So the high frequencies, the low frequencies are located here on the edges, okay? These are low frequencies, and these are high frequencies, okay? So if we want to apply a low pass filter, we have to multiply with 0 these edges here. Okay? If you want to multiply a low pass filter. And then let's come here. Now that was the unshifted version. Now using our terminology for this class, let's see the experimentally measurable quantity. The only thing that we add is that here we add an FFT shift. Okay? So we just shift the data which was the F. So if we evaluate this, this is what we observe. So initially, what did we say before while? We said that this one being the image, we get this, the Fourier transform. We call this one the mathematical construct. And this one here is the experimentally measurable. Sorry, this one here. And this one, it makes more sense because it's impossible to have an image where we have the low frequency components. And the low frequency components, they are right here in the center. But because of this high rate of periodicity, we see a lot of beautiful or equally located spots everywhere in this image. Then what remains for us to figure out is to do the following. So for example, we want to determine, let's see here, we want to determine where is the bright spot that we want to take out. And actually, the ones that we want to take out that have the highest effect would be the ones that are very close to the center. So in this case, if you want to remove this one, which has a location, let's find the brightest spot, 0.83, 0.83, 85. So this spot it's 4826. 4826. We go to the filters. This is 4826. This is the location of this spot. But let's not forget that this spot that is 4826 here, this belongs to this spot down here. Because of this FFT shift thing that we're talking about, okay? So, but the filters, we can multiply the filters, the notch filters here with this region here. Now, this is 4826. Let's pick up a symmetric one in here. So let's pick up this location here, 0.72. 72, it's 83, 83. Okay, this is 554, 554, 456. 554, 554, 456, 456, 544. Okay, so here we have a couple of filters that we want to generate them. If we generate them like this, we go to the filtering, and since we generated just two, we can do the following. We can show like this. Image filters, we evaluate this. The filtered image is right there, and we want to have a look at how it looks like. So this filtered image, let's see, this was the original image in the Fourier domain, and this is the filtered one. So we have the darkened or we have taken away this specific spot here. Now, if you want to remove all the frequencies, it looks like here we have a lot of spots that we want to zero out, which means that we have to take this, this, and we should start with 1, 2, 3, 4. So we first start with the brightest spot very close to the origin. And something which happens in Fourier domain is also this. If you have a bright spot right here, this is like 10 hertz. We also observe 20 hertz, we observe 30 hertz, we observe 50 hertz, 60 hertz, and more, okay? So since this periodicity is everywhere, we see multiples of cosine theta. So if you take in the mathematical aspect, the expansion is always cosine nx, or n frequency, n times a specific frequency. So if 13 hertz exist, we should have also the 26, the 39, and all of these multiples of the frequency. Now, I think it might be a little difficult to show how we work with this code here, because we have to identify a lot of spots as we all saw together. Now, let's see a couple of other examples. And this time, we want to show the application of some other filters. And the filters that we can talk about, that we are going to talk about, is an ideal filter. An ideal filter, it's a filter which is just 0 and 1. So we determine a specific. So let's have a look here. Actually, let's try to run the same example that we had before. So we have this money with some noise in it, and we want to apply a filter. But this filter, it has we can determine what is the k vector. Now the k vector, if you can see here, this is the width of the filter, and this k vector, I think I made some notes. So this width, we can see this one in when we take the Fourier domain. So this is the radius, because we said before that in the k domain, the frequencies all appear centered at 0, which means that this 64, it will be the radius. So we should have a circle with a radius of 128 pixels when we observe this image, but not the image, but the transformation. But I think it will become clear in a moment. Here, m and m, they are the dimension of the size of the image. So now that we know this, let's develop an ideal filter, which is, oh, no, that was a mistake. Sorry, this is like this. Evaluate. So this is the filter that we are generating, and we can have a look at what these filters look like. So this is what it is. An ideal filter, it's a function which is going to multiply with 1 the components in the middle of the frequency domain, starting from 0 and low frequencies within some range. And the higher frequencies will be simply multiplied by 0. So in 3D, this is how it looks like. This looks like a very sharp head. So this is this filter. This is ideal. It's just ideal because it's jumping from 0 to 1, but it's not ideal in terms of that it operates, because this brings a lot of ringing effects, because we don't want, because such a sharp edge in the frequency domain, this will bring very low resolution in the real domain, okay? So we have this, the Gaussian functions, if we switch from real domain to the Fourier domain, there is something which they are inversely proportional. But let's continue here. So we had that image, and this image, let's see how it looks like. Now, a lot of these figures, you can run the codes a little later on your own. They are all the same, but we're just trying to using some operators to make them much clearer. So here we observe this is the unshifted version. As you can see, this is the shifted version, which is where we see these frequencies that appear around here, like here, here, and in these regions. Now we multiply with a filter. The filter we generated, we know how it looks like, right? It was 1 in the center and 0 everywhere. So that was how the filter looked like. We multiply them now. Now that we multiply, this is the filtered image. The filtered image, let's have a look at figure 14. Now at figure 14, this is what we get. Okay, but let's see what was, this is the filtered image. why do you observe this? That's the question. So filtered image is f times the filter, but f is the unshifted version. So f, I think it's something like this. So we are observing the center of this one, and we are multiplying with the filter. But now, let's see what is this. The clean image, it is the filtered image taken the Fourier transform. But now let's have a look for a moment. I think it was clear before a while when we were discussing regarding the. So in this example, we are going to see a little. Let me stop presenting just for a moment. Let's have a look on the board. So in the couple of 3 to 4 lines of the code, what you are going to see is that we generated the filter, which was the ideal filter. If you look at this ideal filter, this was 1 in the center and 0 everywhere. Okay? So this was the ideal filter. It comes like this. And now, but this is centered at the k0. So right here, this spot, this belongs to the k equal to 0. This is k equal to 0. And now, when we are going to apply the filter, we can apply, since the filter is centered at 0, we cannot apply this filter in this domain or in this mathematical construct. We should multiply here in a shift version, in the shifted version. Because if we multiply with this filter right here, it's going to be 1 here and 0 everywhere. But let's not forget that the low frequency terms, they were somewhere here. These were the low frequency terms. And these low frequency terms, we find them respectively here, here, and here. And these specific filters, which is called low pass filter, I mean this ideal filter that we just generated, it's a low pass filter. So since this is low pass filter, we should multiply with 1 small numbers and multiply with 0 large numbers, okay, or high frequencies. Now, so in this example, we intentionally kept it as it is in the code. So let's, and also always try to remember this, that we have the image FFT2, you go to FFT shift, you multiply here with the filter, and after you multiply with the filter to see the effect of this filter in the Fourier domain, we should go backwards. How do we go backwards? We go like inverse I FFT shift, okay? So we go to the mathematical construct, and then after here we take the inverse Fourier transform, IFD2, inverse Fourier transform 2. So we should, in order to do a good analysis, we should always know where we are, where our data is standing. So let me share the screen again, and let's go to where we were. And as we said, we are here, we're doing kind of a mistake because we are multiplying the filter with the high frequencies that are in the center. But, and now this image which is filtered, image filtered 1, we take the Fourier transform here and we look at the clean image. The clean image is going to look something like this. Okay. It is gone, okay? Now, we see nothing of the image, which was this nice banknote, Albanian banknote, because we have kept only the high frequencies. And we have wiped out the low frequencies because the low frequencies were standing out in the edges. Now, the most, I think, let's see here, what are we showing here? I think figure 16, let's see what we get here. Figure 16 is the filtered image, is the FFT shifted, so that's why we see this. And this is the multiplication of the, okay, so this is, we have multiplied the image with a filter, and now the most important, wait a second. We have something like image filter 2. Where is it? Okay, okay. Okay, now let me clarify this one. We had the F, which was, so figure 16, it was, let's, okay, again, figure 16 is this. So now we have shifted the data, Okay, we have shifted, and now in this image, if we multiply with 1 in the center, we are going to preserve most of the image. Okay, so we do, let's run this again, it doesn't matter, we run this again. So this center, we're going to multiply with the filter because this is the filter, H, and in figure 17, we have this image filter 2, this variable here, we are plotting it here in figure 17. Now this figure 17, oh no, okay, this is not, this is the Fourier domain times the filter, okay? This is very essential. So you can see from here that these high frequency terms that we see these dots here, they have survived, okay? So these, the most dominant features, they are still there because the filter was wide enough. And since we selected the K as 64, most probably we should get, using the data cursors, a diameter of 128. So if you see this edge, which is 90, around 100, this is around 96, around 100, we go to the other side, we get 224. 224 with around 100, it's twice the 64. And then, now we have a look at this. Okay, this is the answer. Now, here, we observe the correctly filtered image. So we have filtered the highest frequencies, and what have we shown here? I've said that the image, I have the image filter 2. Image filter 2, it was filtered correctly because here the Fourier domain, it was shifted. After it was shifted, we had a low frequency in the center. They were multiplied here. Then once we get this filtered, but it's in the Fourier domain, we do the shifting, and then we do the inverse Fourier transform, and then we plot the real numbers of it. And finally, we get something like image clean 3. And the image clean 3, this is going to look like this. Okay, so this is the original, the image that we are moving around. Now, let's have a look again. Let's make this 20. So if we make this, let's make this 32. And the most important image here is that, not most important, but one that teaches us a lot is image 17. Let's try to identify where this image 17 is. I cannot find it. Probably we close it. Okay. Anyway, we can plot everything from scratch, but things can become slightly different if we change this K as 42. Or things will become much better if we go like this. We clear everything, we run this. We have we find the width of the filter. Evaluate selection is 32. We generate an ideal filter. Oh, no. This is we generate this ideal filter. This filter, which is now smaller in K. So this is how it looks like, and we know how this was here. This is our ideal filter, an abrupt change from 0 to 1. And then we follow all the same that we did before a while, with some testing phases in between. But as we said before, we might focus on figure 17, that I picked it correctly here, because here we see that we have multiplied, this is the shifted version, and we have removed a lot of frequency components here on the edges. Okay, now you can play around with these, and at the same time, we can use other filters than the ideal filter. We can use a Gaussian filter, and a Gaussian filter, it's a smooth one, which we traditionally use this a lot. So if we use a Gaussian filter, and if we look at how it looks like, this is how it is. Okay, it's not anymore like an abrupt change from 0 to 1, but it's smoothly, so this is how it looks like. And now with this Gaussian filter, we can also check what, and we should get comparably similar results. And again, figure 17, which should be a good measure or to look what we are really doing. So this is the image in the Fourier domain. This is the filter that is multiplying 1 here and gradually changing 0.5, 0.10 around here. And this was, now we can also use another filter, which is the Butterworth filter. And this Butterworth filter, it's something which is between, we need another parameter. And the equation of this one, we need a k, and we need also a parameter 2. And this parameter 2, it's just something that appears in the denominator of this function, which I'm going to talk about this one. And the Butterworth filter is something which is between a Gaussian and the ideal filter. So if we increase the p, so if you see here, this is like a Gaussian because it's smooth at the top. But if we change this p value into a higher p, let's make this 5, and we generate this Butterworth filter again, and with selection, and then we have a look at these. So now this looks like an ideal filter, which means that this really looks like where it's changing abruptly from 0 to 1. And we don't like this a lot. We like to have a smoother, a much smaller change or gradual change in the k domain, because with more gradual change in the k domain, this enables us to have a low resolution in k, but we have also a higher resolution in the x domain, in the images, okay? So asking for the best resolution in the Fourier domain, that means that we lose everything in the other side. So here we come again. This is our image 17, and I want you to go over all of these results that we have shown here, especially this part of the code. It's good if you go over again this one, if you go over this one again. Now let's see how we can do the filtering in this pattern image that we had before, that we dealt in the previous example. So let's clear everything. And let's see how this image looks like. So this is the patterned image. And then we generate, so here, I just wrote before that if we use K20, so this, let's assume that K is 32. K is 32, and let's evaluate this, and let's make an ideal filter with this width, evaluate selection. And with this filter, we know how it looks like. We're not going to plot it again. But let's see what figure 17 tells us. And in this code, figure 17, here we have it. So figure 17, what we see from here is that these features, which are, so this is the filtered version, okay? You can have a look later on here. But this is the shifted Fourier transform, or the original image. And we are multiplying with this filter right here. Now, if we use different k's, the values of k, we can filter, if we use a k of 20, we can wipe out this periodicity in the x-axis, okay? But because we are going to leave this out, so let's see how figure 17 looks like if we set the k equal to 20. So here we have this k value of 20. We generate the ideal filter, which is here, evaluate selection. And with this, we go again, we evaluate the selection, and figure 17 is going to look a little slightly different. Here we are, this is the 17. So this image 17, we see that we have wiped out a frequency in the x-axis, so we have completely removed one periodicity along one domain. So this is the final result if we filter out all these frequencies, okay? And this is the filtered one. If we use a much smaller k, where we filter out also the rest, so, but this is something that you need to analyze carefully. What happens if we use the k10? Because when you use k equal to 10, it's true that we wipe out much more frequencies in both axes, x and y, but something remains for you to analyze regarding the final result. So the final result is this one, and this is the figure 17, where we clearly show how we are removing the specific frequencies. So in here, look into this, we are really removing this frequency, which is high frequency here, this one, sorry, this one, this one. So around here, we are preserving just the lowest frequency components, which is right here. But since this image is full of periodicities, or is very periodic, we lose the features themselves. So it's not that it has a pattern and you have some oscillation convolved with the image in the real domain. Okay, so spatial frequencies or patterns that are periodic in the real domain, when we take the Fourier transform, we see this specific bright spots, or let's say specific spots in the Fourier domain. So this was the second example that I wanted to go over, and in principle, what you may need to go over again, but I think I can also explain here on the board, is to have a look from the textbook and see how the filters are defined, or we can have a look here together. So the filters that we dealt today, we have the ideal filter. An ideal filter is this one that we have shown here. The ideal filter is 0 and 1. Okay, so all ideal filter is about is that we assign, you make a matrix full of ones, okay, and then we say that if a radius is smaller than some relative radius, if we make these, we make all zeros. We make all zeros, and if distance is smaller than some d0, if we make those ones, this is the ideal filter. The Gaussian filter, we know how it looks like, but the Butterworth filter, it looks like this. We have a function which is UNV, and the x and y, I think I should have done this before. So if this is x and y in the image real domain, when we come here, this is going to be the u and v, okay? And u and v, they are like the conjugate quantities, or the reciprocal quantities, or the transform quantities of x and y in the Fourier domain. So now, this h, which depends on u and v, this is going to be equal to 1 over a large denominator. And this large denominator, for the sake, so that we don't have a division by 0, we have a term which is 1 plus duv, and this duv divided by d0 to the power 2n. Now, this p value that we change in the code is this n actually. And as the n increases, this Butterworth filter, this BF Butterworth filter, this converges to ideal filter. So as n increases, this becomes ideal filter. Okay. As n decreases, the Butterworth filter, this converges to a Gaussian filter. And there are all these are all linear filters. So this is what the filter looks like, and this itself, for every point in this domain. So for any specific UV, let's assume this is U58, V57, okay, which is a location here. This is going to be, we can write this one, the PUV. It's a matrix, or it's an array, which is equal to square root of U minus P over 2 squared plus B minus Q over 2 squared, all square root. Okay? So this is the filter itself here, 1 over this whole denominator, and this is the matrix or the array that we observe here. And every element of this array, this matrix, which is a 2 by 2 matrix, it is divided by a normalizing factor. So if this one, and then we have also this term. So this is the mathematical way how we write it. And in order to generate that specific filter, you cannot, you can use the codes that they are provided for you. Okay, so this is all for this session. But I want you to carefully or to monitor what we have on the board. And finally, or I can always try to, so what you have here on the board, always try to identify the following. We have an image, we use the Fourier Transform tool, we get the IFT, the image in Fourier domain, then we take the FFT shift
So we should know where we are, and we get IFT shift. And then if you want to go backwards, we should follow the inverse operators that we did like this. And here, we can multiply here with some specific filters. And finally, we can get an image which is filtered. But the filtering is done in the Fourier domain. So the filtering is done in this complex domain here. But we observe the changes in this other domain. And now the filtering, this can be used also for, so here, the filters that we explained here, they were low-pass filters. And a low-pass filter, so for example, the Butterworth or the Gaussian filter, they look like this. They look like, so we have an array, and this, let's not forget, this is in the K domain, and this is the Gaussian and Butterfield, they are very close, they look like this. And these are called low-pass filter, LP. So this can be called like Butterworth low-pass filter, BLPF. Now, if we want to have a high-pass filter, what we can do, a high-pass filter, it is equal to 1 minus the Butterworth low-pass filter. And then what we get is the following. Let me try to find a different color. So here, the filter, if we do 1 minus this, it's going to be 1 everywhere. So this is going to be a high-pass filter. So they are easy to generate. So if we write this one, if we can find the filter, which we showed this one when we did the exercises on MATLAB, you simply just do this, you multiply the image with this, and we can find only the high-frequency terms. And what we learned in the previous chapter is that these high frequency that are preserved now, we have an image which has only the high frequency terms. And for this, these high frequency terms we can use to enhance the image that was originally in the real domain. So again, low pass filters, it's easy to get the high pass ones just by taking 1 minus the low pass filter. Okay, so this will be all for today, and see you in the next session.